Good afternoon, everyone. I'd like to thank you all for joining us today in our weekly webinar series. Today our featured topic is fiber optic system design. My name is Jessica Petrohoy and I'm the marketing coordinator at fiberoptic.com. Fiberoptic.com is a leading provider of fiber optic products, training, and rental equipment. We're pleased to present this topic to you today. So with us today to talk about fiber optic system design is Terry Power. Terry is one of our senior instructors and a field technician with over 25 years in the managing and testing networks. When Terry is finished, we'll take questions from the GoToWebinar question box that's at the bottom of your screen. We'll have a question and answer session. Remember that our webinars are always posted at fiberoptic.com/webinar. And thank you again for joining us today. And at this time, I turn the presentation over to Terry.
And good afternoon, everybody. This is Terry Power. A little bit of my background, I guess, before we get started. Jess had mentioned that I've been doing this for 25 plus years. I started doing cable television work in 1987 after coming out of the Air Force, where I'd worked on microwave radar jammers. And as fiber pushed deeper and deeper into the cable plant, I started moving more and more over into the fiber. And by 2005, I was working down in Barbados and became outside plant coordinator for Tele Barbados. In 2007, they sent me to fiberoptic.com to get a certification, and I struck up a friendship with the president of the company, consulted with him on some other projects after I went back down to Barbados. In 2009, I moved back to North America, and Chris put me on salary, and I have been with him since. In the time I've been here, I have run cable crews throughout the Northeast, have done testing jobs throughout Central America and the Caribbean, and have taught classes on 4 continents, including regular trips to Dubai. I have been to South Africa, Nigeria, Kuwait, as well as classes all over North America and the Caribbean. So that just gives you a little bit of a background on me and where I came from and how I got where I am. So let's see. Today we're going to talk about fiber optic system design, and we're going to start with part 1. This is going to be a 2-part series. For today, we are going to talk about planning the network. We are going to talk about operational requirements. We're going to talk about fiber types, the physical environmental requirements for our designs. We're going to talk about inside plant routing and outside plant routing. In our next presentation, we will carry this to another level, and at the end of this presentation, I'll give you some of the topics we'll be talking about next time. So let me see if I can get this thing to go. There we go. So fiber optic design, planning a fiber optic network. First thing you're going to want to do is a feasibility study. And I will tell you right now that I am not in this presentation going to give you do this, do this, do this, do this to create a plan. I am going to tell you a lot of questions that you need to ask. And I'm going to help you to understand the questions and understand the answers you get when you ask those questions. Planning and designing are very specific to the individual and to your project. So there's no hard, fast rules for you must do it this way. By asking the questions, you will determine what you need to do with your design, with your system, and that could be different from system to system. In fact, I expect it would be. The design work and the layout that I did for one of the local municipalities is completely different than some of the consulting I have done for longer range projects in Florida, and very different than what I did with the layout and design work in Barbados. Every system, every project is going to have different questions, different answers, and certainly different solutions. So the first thing we're going to be asking, though, is what are we trying to transport? What is our package? Are we sending SONET SDH? Are we doing Ethernet? Is it going to be fiber to the home? What kind of information are we sending? We're going to look at whether or not existing copper infrastructure can do the job. Probably not, or we wouldn't be looking at the use of fiber. Are we going to upgrade existing systems? Is there existing fiber out there? Do we have a way that we can upgrade rather than installing a new system? If we do have to install new fiber, then we're going, and all the hardware associated with it, then we're going to have to look at our rights of way costs, our hub location costs. Are we going to lease or buy these locations? Are we going to build our own pathways, or are we going to lease existing pathways? What are we going to need for pole attachment agreements? All of these questions about the path actually do lead back to the initial question of whether we're going to try to upgrade or whether we're going to go new. Because new has a whole set of variables that have to be dealt with to determine the cost efficiency. So some operational requirements. Again, we come back to the initial question. What are we transmitting? Are we transmitting data? Voice, video, telemetry? Again, we come back to SONET and SDH. We have fiber to the home or fiber to the X, fiber to the whatever. All of these questions about what we're transmitting have to be answered. As you can see from this graphic, something as simple as a fiber to the home or fiber to the business, FTTX, is going to have as many as 3 bandwidths, where you're going to have your 1310 nanometer downstream that's going to have your voice, data, and any kind of IPTV. Then your 1490 is going to go upstream. Excuse me, I got that backwards. That's going to be 1310 is your upstream, 1490 is your downstream. That carries your voice, data, and TV down. And then your 1550 is going to be broadcast video downstream only. So, even something as simple as fiber to the home is going to have some amount of questions have to be asked, and the answer, of course, gives us information about what bandwidths, what wavelengths, and what kind of equipment we're going to need on either end of this fiber. What kind of protocols and architecture are we going to use? Are we going to use a token ring, Ethernet or GigE, asynchronous transfer mode transfer protocols? Again, SONET SDH, fiber channel, hybrid fiber coax. Cable television basically runs a fiber to the node, which is really what HFC comes down to. And then you've got, of course, your PONs or FTTX. So answering these kind of questions, are we going to go with a ring, self-healing ring such as SONET SDH, star architecture such as FTTX, hybrid fiber coax, or a simple point-to-point? I mean, it could be something as simple as a single point-to-point connection. I have participated in the layout of several of those and done a lot of splicing and testing on straight links that go just from hub site to hub site to hub site between cities. We recently did some testing we started in Denver, Colorado, and went from a co-location site to a hub site, and then to another hub site, and to another hub site, and ended up a few days later at a co-location in Des Moines, Iowa. And it was a straight point-to-point shot through multiple hubs. So, that sort of connection is still going on out there. So what is the design that you're going to be doing? What is the architecture? What are your needs? Once we answer those questions, then we can start looking at some of the operational requirements. We're going to look at the standards that we're going to utilize, our transmission standards. Look up what our standards are for sonnet, for loss and dispersion, distances, what our fiber channel standards, FTTX or PON. The FTTX tends to be limited, depending on who you ask, to 25-ish kilometers, unless you go with an active Ethernet protocol on top of the FTTX, which will allow you to run out to 120 kilometers. So all of these things have to be looked at. What kind of installation standards are you going to look at? Are you going to be going with EIA, TIA kind of standards for the US, looking at 568C and 758? The 568C is your fiber optic component standards. The 758 is your outside plant and your building standards. Then the ITU has a variety of standards, G.983, G.984. All of these are about installation of the fiber itself. And then testing standards, 61280, 14763. What standards do you want to use for your testing? Tier 1, Tier 2. Do you need fiber characterization at the level of CD and PMD? All of those questions will need to be looked at, and the cost associated with having either the equipment or the personnel to come do those kind of tests. Also under operational requirements, we're going to be looking at our wavelengths. Are we going to be running short runs, say less than 2 or 3 kilometers? Then maybe 2 kilometers we can push multi-mode and go with a less expensive light source, such as an LED or a VCSEL. Those vertical cavity surface emitting lasers, while they're more expensive than LEDs, are certainly not as expensive as a true laser that's used in single mode fibers. It does have the larger core, and you're going to have more loss per kilometer, but you can operate with those less expensive light sources. If you're going the longer distances, out past 2 or 3 kilometers, you're really going to be looking at single mode. And even inside buildings, I'm seeing more and more and more of single mode fiber being used as building backbones. And it's padded down on the other end, because you're still going to have, even with multi-mode and those short distances, you're still going to have bandwidth limitations. So again, if you've got a very high bandwidth application, you may still end up being better off going single mode and padding it down. Recently did a project that was just that sort of thing. We couldn't even get SFPs that were low enough in transmit power to not saturate our receivers. And the receive side, we had to pad it down, but it works famously because they had the ability to go with a very high bandwidth that the multi-mode fiber could not have handled. So these are the sorts of questions you ask. These are the factors you take into account, and then you find solutions. The single mode is going to give you much less dispersion. You can go, we used to say there's no limits, but realistically now we're looking at CD, chromatic dispersion, and polarization mode dispersion, giving us some limits, but usually you'll see some kind of hub site about every 100 kilometers with no degradation to the system at all. Then you've got to look at, if you're going with single mode, one of the factors for upgrading existing fiber is using a wavelength division multiplexing. If you've got existing fiber that goes where you want it to go, but you need more signals, one of your options is not in the glass itself, but in the hardware on either end. And if you can take one dark fiber and put wavelength division multiplexing on it, you can run multiple existing signals, even with disparate types of technologies. You can run a sonnet on one wavelength and a pure gig-E Ethernet kind of protocol on another wavelength. And something as simple as just a ATM transfer protocol on another wavelength altogether, and that will allow you to expand your system using the existing glass. You can go everything from coarse wavelength division multiplexing, which is up to about 20 channels or 40 channels with a 20 nanometer spacing, up to DWDM, which I've seen some designs with over 100 channels, over 100 discrete lambdas, running between 1550 and 1675, and just packing them in there every 0.8 nanometer. And now those are higher cost lasers. The CWDM will work with your baseline kind of lasers in most applications, and there's a lower cost. Again, everything you do, you can expand, but it's going to cost you. You can go to the laser and go further on single mode fiber, but it's going to be more costly. And there's always that trade-off between functionality, higher function, and cost. But if you're running into right-of-way issues, not having enough pathways, looking at having to get a right-of-way and environmental impact studies, and all of the stuff that goes into then hiring all of the construction crews to come out and dig a trench, and then you've got to shore up the trench, and then you've got to lay in the conduit, all of this before you can ever pull a fiber. And then you're looking at the cost of CWDM to put more and more fiber or more and more signals onto existing glass. You have to weigh those options. If you've got pathways going where you need to go, those are things you want to look at. On the other hand, if you're going somewhere completely new, then you're pretty much going to have to build the new pathway. But even then, you want to look at the future. And you want to look at CWDM and DWDM options for giving you expandability into the next 100 years. Data rates, bandwidth requirements. I've touched on this already. Are we just going with a direct connect? Are we going Ethernet, Sonnet, SDH, 10 gigahertz or gigabits or 40 gigabits? What is it we're going to need? That's going to have an impact on the equipment on each end. That's going to have an impact on the type of fiber you have to buy, on the distances that you can go between hub sites. So All of these questions will need to be answered and factored into your hardware on either end of the fiber. Now, mentioning fiber types. I've touched on this briefly, but let's talk a little bit more in depth about our fiber itself. Legacy multi-mode. It's called OM1 and OM2. This is the stuff that was out there from really, I guess, close to the beginning. OM1 had a 62.5 micron core, used ST and some SC connectors. Basically, your 10 gigahertz length is 33 meters, maybe 100 feet. That's it. Then the standards were tightened up. The ability to manufacture a smaller core came into play, and we dropped down to a 50 micron core, which is, by the way, the international standard. That's the standard we have on most of the ITU international standards and what I deal with when I talk to people in Africa and the Middle East. That had it gave us the ability to have the length stretched out to about 250 feet. Really what it comes down to. Getting close to 300 feet. Then they changed the glass again and came out with OM3, which is a 50 micron laser optimized. And this is usually defaults to an LC connector. It uses a vertical cavity surface emitting laser. I usually say VCSEL because it's a whole lot shorter to say than vertical cavity surface emitting laser. So the VCSEL allows us to push out to 300 meters. And then the OM4 is another laser optimized that uses a default with an LC connector, but it can push us out to about 550 meters with a 10 gigahertz or gigabit bandwidth. So let's see, the OM1 had the 62.5 micron core, numerical aperture of .275, lets in a ton of light, but it lets in a lot of extra modes, so you do have the capacity for modal dispersion that you need to deal with. Attenuation of 3.5 dB per kilometer at 850. If you go up to 1300, you can cut that down to 1.5. But again, your bandwidth limitations, 500 megahertz per kilometer at 1300 nanometers, again, is going to cause us to be limited to about 100 feet, 33 meters, with any kind of bandwidth. OM2 has the 50 micron core, numerical aperture of .20. Attenuation is a little bit better here, particularly at 1300. You've got that .8 dB per kilometer, which allows us to stretch out to 83-ish, depending on what chart you look at. Looking at the previous chart, it was 83 kilometers or 83 meters, which is going to give us, what I said about 250 feet with a bandwidth of megahertz per kilometer of 1,000 megahertz per kilometer. So we're getting a little bit further out in our reach. Now OM3 and OM4, again, because of the 50 micron core is going to have the .2 for the numerical aperture. Our 1300 nanometer attenuation is going to be around .6, and we can get those higher bandwidths down around 850, we can get some pretty good bandwidth. But again, we're going to be limited by dispersion and just the loss. And the bandwidth limitations are going to be far in excess of single mode. So, single mode fibers. We talk about G.652. Almost everybody nowadays talks about the ITU-T standards. And so all of these, I'm going to not say ITU-T every time just to save us all hearing me rattle. We're just going to talk about the G. It's G.652, 652A, 652B, and C, and we're going to look at each one of these. Those are pretty much your standard single mode fibers. Was that 652 series. The exception is the 652D, which is a low water peak. And what happens is with the original fibers, there was the introduction of hydroxyl ions in the manufacturing process caused water peaks in the response curve. So I think it's somewhere around 1283. I may have a slide in here to show you that. But anyway, that water peak prevented us from using the entire spectrum for coarse wavelength division multiplexing. The 652D low water peak diminished those water peaks, never took them away completely, but it did make those wavelengths usable so that we could have a standard channel spacing of every 20 nanometers from down around 1300 all the way up into the 1600s in our wavelengths. Okay, then we discovered that 1550 had the least attenuation of any wavelength. And so we remade the glass and we came out with the 653 type of fiber, which is dispersion shifted. And that moved the zero dispersion wavelength, commonly referred to as lambda zero. It moved that from down around 1300 up to 1550. And that caused some problems when we started running wavelength division multiplexing, because then we had not enough dispersion, not enough chromatic dispersion, and it allowed for four-wave mixing, which was the creation of a spurious signal. And if you attend one of my workshops on wavelength division multiplexing, we'll get a lot more deep into that topic. But trust me when I say that it caused problems. Every time we solve a problem, we find a new one. So then they came out with non-zero dispersion shifted, which was the G.655, that moved the lambda zero down to about 1490, which allowed for a small amount of dispersion, of chromatic dispersion in the C band where we were doing the dense wavelength division multiplexing, which greatly diminished the four-wave mixing components and allowed us to go further and faster. Because let's face it, most development in fiber optics is always about going further and faster. How much bandwidth can I pack into a piece of glass and how far can I push it without having to do anything to it? I mean, that's really what it comes down to. If we can get a single piece of glass to carry everything we need as far as we need it, and all we need is equipment on both ends and we don't need anything in between, we win. We keep costs down. So everything's about going further and faster. And the last fiber type I want to talk about is the G.657. It's a bend insensitive. Any of you guys that have attended any of my previous webinars, you know that I talk about bend radius. and the effects of overbending, macro bending we call it, on the higher wavelengths. And again, when you're looking at going further, faster, we're up in the 1550, 1625 band wavelengths, and that's where we're going to have the most loss from bending. So the bend-insensitive fibers were developed to help combat that issue. They've got some that's designed for outside plant, but the most common type of usage I see with the bend-insensitive is in patch panels, because slack management in patch cords is one of the worst things I've seen for bend radius or maintaining good slack management. And the bend insensitive patch cords provide us with a little bit of protection in regards to macro bends in patch cords and in head end locations. And I was right. We do have a slide about the water peak. Now, if you take a look at this graphic, that top row with the larger dots, that's the original water peak. And I was wrong about the wavelength. It's more like 1383. But that water peak wiped out a whole section of wavelength that was not available for use in coarse wavelength division multiplexing. So the 652 through the 652C had the 9.3 plus or minus 0.5 micron core, very often referred to as 8 to 10, because it's somewhere around, new standards are like 9 plus or minus 1. At a numerical aperture of 0.13, which means it's not letting a whole lot of side light coming in. You got to hit it right up the middle. Attenuation, that 0.4 and 0.25 at 1310 and 1550, really not what you would expect these days, but with the older glass, those are a little high for contemporary standards, but like I said, with the older glass, that's not too bad. And then our dispersion was originally, we had very little dispersion at 1310 and a huge amount of CD. And this particular dispersion is chromatic dispersion, measured in picoseconds per the nanometers times the kilometers, very often just referred to as picoseconds. But 3.2 per kilometer at 1310 is not much, but that's 17 at 1550 very soon. With over a very short distance, high bandwidth applications were not being usable because of the pulse spreading. So, a little bit more about the types of optical fiber. Another couple of drawings here. This is one of the better drawings that shows the relative size of the two cores. And these are pretty accurate and to scale. So you can see the huge core in a multi-mode fiber. You know, it says on the slide large core relative to the cladding. I think of it as huge. It just looks massive. Half the diameter is core. Down with the single mode, the real core is probably closer in toward that very light to white area, with the mode field diameter being stretched out a little bit more to that orange line, where there is a little bit of light traveling in the cladding as well as in the core. Multimode was the original fiber type. It's used in local area networks, again, short runs. Uses relatively inexpensive light sources such as LEDs and VCSELs. Has multiple paths of light. Every angle that light comes in to that core is going to create a path. And those paths are going to propagate at different speeds. And over distance, you start getting what we call modal dispersion. Now, single mode, used for wide area networks, backbone systems, that's the long runs, uses the more expensive but certainly higher bandwidth laser light sources. And because laser is truly coherent light, we have a single path of light. So we don't have the modes spreading out or propagating at different speeds. We have a single path of light. Now, physical requirements and environmental requirements. We're going to talk about 14 steps. We're going to map the network. We're going to look at the cable route. We're going to look at hardware locations. Where are we going to put our enclosures out in the field? Fiber distribution cabinets or hubs, splice enclosures. We got to look at every one of those locations. Make sure it's accessible. Make sure you can get to it. Make sure it's not in the middle of a intersection in a manhole with two 6-lane highways crossing. Move it around the corner and up onto the side of the road. Make it easy to get to with minimal impact on traffic, because if you have minimal impact on the idiots behind the wheels of vehicles, you will have safer technicians. Straight up. I have worked on the side of the highway in a variety of countries all over this planet, and there is no place on the world that drivers with their hands on a steering wheel are not stupid people. There's nowhere on the planet that I have felt safe being out in the middle of the road. I try to get my setup as far from the road surface as humanly possible. Just easier access, and it's safer for everybody involved, including the idiots with steering wheels. Then our optoelectric locations, whether it's going to be the two ends, are we going to have repeaters or regeneration stations in between? Are we going to have nodes? Cable, central offices, head ends. Are we going to have, shacks every 100 to 150 kilometers where we actually receive and repeat the signal? So are we going to have amplifier locations? All of this has to be taken into account when we're looking at the map, at the physical geography of the system. Then we got to think about where we're going to place it. Are we going to place it in the air? Or are we going to place it underground? If we are aerial, are we going to lash it? Do strand and lash? Which of course gives us the capacity for expansion, because you can always go back and overlash on an existing strand. Or are we going to go with some sort of self-support? Self-support gives us a couple of benefits. It's less costly to install, but we don't have the capacity to add to it. We have to run additional hardware and start the process over if we want to run a new fiber. Also, depending on who your client is, recently did a project with a municipality I mentioned earlier. They also owned the power company, so they had access to the neutral space above joint use. So by using self-support, it was all dielectric, we could safely and within the standards and the proper installation technicians, they could actually install this fiber up in the well, not quite energized space, but in the neutral space above where joint use installers are allowed to operate. And it freed up a great deal of space that was available because they used self-support. We could not put conductors such as strand and lash up in that space. So these are questions and considerations for you to think about. Again, this is about asking the right questions. Now, if you're going underground, are you going to be ducted or are you going to direct bury? I will tell you my preference is almost always to put it in duct. My preference is always to put in about 4 times the number of pipes I think I'm going to need. Because A, I'm going to need more later, and B, someone else might want that route and might be willing to lease it from me, in which case I now have a revenue stream on the construction, and that's going to cut down on my other operating costs because it's going to be offset by someone paying me to use part of the duct. So again, those are considerations when you are doing the design and layout. Now, the inside plant, where are we going to put it? You can see here, this is a pretty standard cable tray. This was running along the top of multiple racks. And each one of those clusters of 3 ran down to a set of patch panels. You could have cable trays, you could have interduct. Now this actually, this installation that you're looking at in the image went away from the camera. It changed elevation down, turned to the right, and then it went down into ducting. And then those pipes took it to 2 different locations where the outside plant fibers came into the building. And there were 2 separate sets of cabinets where we spliced the outside plant to the inside plant fibers. So, cable trays, how are we going to run it? You got to think about all of this when you are looking at your layout, not just outside but inside. What kind of environment are we going to need inside? We're usually going to expect to have a more consistent environment for temperature, humidity, etc. We could have very often possible multiple moves, adds, changes. We're going to expand. Maybe we bring another fiber into that building. So we want to consider the room being big enough rack space for additional fibers. That's one of the reasons we went from the larger connectors down to the small form factors such as LC, because we end up running more and more fibers into the same closet, and the closets ain't getting no bigger. So we're going to have to go to smaller connectors that we can pack in more tightly. As you're designing your layout for the future, you want to look at what you can do to provide yourself expandability in the future. Make sure your rooms are big enough. Make sure that if you're going to be adding active equipment, that your environmental controls are sufficient, not just for today, but maybe I have twice as much equipment in there 2 years from now. Is the existing AC going to keep that cool enough when you double the heat production? So you have to look at the future. You always have to look at the future. Outside plant, we've got to look at devices and enclosures and cables that are designed for vast fluctuations in temperature. There are parts of this country where I have worked where I could have below 0 temperatures for lows in the winter and 90-something degree temperatures for highs in the summer. And every piece of equipment between buildings has to be able to adapt and to handle that diversity in temperature, not just daily, but over the year, and sometimes daily, sometimes 20, 30 degree temperature swings, winds, storms. I worked a lot in Florida, and I promise you storms is something you think about every day down in Hurricane Alley. But you got to remember it's going to be harder to perform moves, changes, and adds. That's why I'm always recommending in outside plants you have tons of slack, 10 to 15% of your trench or strand footage should be added as slack, so that if you ever do have to do a pole line transfer or anything like that, you've got slack that can move across the road when they decide to widen the highway and move all the poles to the other side of the road. You've got slack to do that without having to splice in more cable. You know, which sounds like an easier process. Take down some slack loops and move it all across the road with new strand, or cutting in splice, multiple splice locations for possibly large fiber counts. That slack could save your backside. Again, temperature changes, weathering effects of outside, ease of access to the cables. You always want to think about your ease of access. Your jacket material. Now, jacket material is going to count for density in ducting, whether it's inside or outside duct. The jacket material, some jackets are going to slide against each other better. Some are going to be a little more rubbery, which is going to give it a lot more drag and a lot more tension. So that's going to cut down on your fill ratios and how much you can have inside a duct. And then you're going to look at fiber placement. How deep are you going to go? Where are you going to place it? Looking at your manhole locations, pull box locations, splice locations, all of this to make it easy to get to and work on. Just because it looks good on a map doesn't mean it looks good in the field. What equipment am I going to use at my locations? Here you can see in the image a rack-mounted distribution box or distribution panel. The splicing to the pigtails would take place in the environment behind those connectors, and we would plug right into the back side, and that would give us access to the fiber for testing, for hooking up to and transmitting. You want to look at the size. You want to look at if you're going to use racks or wall mount. Power requirements for your transmission equipment. What kind of power am I going to use? Am I going to use AC or am I going to use DC? What are my voltage requirements? What are my backup requirements? DC gives us the advantage of having battery banks for backup that will give us several hours to days of backup power. And a lot of equipment will run just as happily on DC. And for those few things that you do need AC, we can always run inverters to take it to an AC level. Access outside. You have to consider rough terrain, secured buildings. We had one location in Connecticut that looked beautiful on the map, but it turns out that it was on the side of a rock face, and you couldn't really get to that splice location. We also had a splice location that was in a parking lot of a very busy office complex, and so we were constantly struggling to get access to that anytime we needed to be in there. We want to look at these things, walk out our design, and make sure that, think about it as if you're the one that's going to have to get to it. Am I going to want to go there? And try to make this as easy as possible for the guys in the field. I guess me having been the guy in the field, now being the guy that's doing the design and layout, I tend to be a little more thoughtful about such things. I tend to think of it as I may actually have to go out there and go up that pole or go to that location. And so I try to make it as easy for whomever, just in case it actually is me. Inside plant routing. A couple of things. Here's some guidelines and then some questions to ask. Obtain Architectural drawings. Architectural drawings will tell you all kinds of stuff about where duct, for air conditioning duct, what obstructions you're going to find, um, where are your firewalls that you're going to have to do fire penetrations. You want to contact the building owner or manager, set up a site visit, take a ton of pictures. Be like a tourist. Click pictures of everything. Even if it's, of only moderate interest, take pictures. It's better to have 100 pictures and need 10 of them than to have 10 pictures and want 20. So, identify everything that you can take a picture of. Where are the equipment rooms? Where are the existing routes for existing communications cables? Where are the, Cat 6, Cat 5? Where's their existing routes? Can we follow them? Or are we going to have to create new routes for the fiber? What obstacles? Again, air conditioning ducting, environmental ducting in general, and firewalls are two of our biggest obstructions and obstacles. Elevators. I've been amazed at the number of times that an elevator is right in the middle of the pathway I want to take. And now I have to find a way around it because you're sure not going over it. So, these are all the things you want to look at. Then what kind of slack or what kind of cable management am I going to use? Am I going to use ducting? Am I going to use a ladder rack? Your standard, ladder rack. Probably the most common and often used out there. Spine trays. Spine tray is, if you picture the old cartoons and you see the scenes in the desert with the rib cages of the dead animals out in the desert, that's exactly what a spine tray looks like. It's a long spine with ribs on it. It's hinged between segments, and it allows you to make curves and changes in elevation much more easily. Mesh trays gives you an infinite amount of possible variations and customization, but they're a little more expensive and a little harder to install. And again, determine your AC and power availability for the rooms that you want to use. And look at the future. Once you identify that equipment room, does it have the HVAC and power capabilities for today and for double or triple what you're putting in there today? Can you double or triple the heat given off by active equipment, and that HVAC still handle that heat? If you want to add more equipment, do you have the electrical power capability? Is that there? Again, it's about asking questions, looking at what you're going to need, and making decisions about today and the future. Now, a little bit about outside plant routing, and I think we're going to start wrapping up after this and take some questions. So make sure that if you do have questions, you put them in the question box, and I will get to those right after we finish the presentation. Outside plant routing, you want to obtain topographical maps, not just flat maps, but you want to see elevation. You want to see where that pole looks like it's a beautiful straight line, but it's actually 200 feet up in the air off the next one. What kind of rises, curves, valleys is that 500-foot span? Well, that looks like a nice, easy one until you realize it goes over a gully. Those are the sorts of things you can get from a topographical map. Are you going to go aerial or underground? Again, direct bury, which is never my first choice, or are you going to bury conduit? Direct bury does have some benefits in cost, and you can usually use a plow to lay it, rather than having to dig a trench. So in fairness, while I don't like it, there are times when it is the most economical. So I will concede that point. You want to mark out the route on the map, your proposed route on the map. Then you want to walk it out. And you want to look at every location. Again, you want to look at that station as if you're the one that's going to go and work there. Do I need to move a splice location to get it on next to a parking lot where I can set up my trailer or my tent in a parking lot and not be out in the road? Sometimes it's that simple. Move it back one or two spans in either direction, and now I've got a beautiful place where I can get to it easy and not be an obstruction to traffic or be in danger. Take pictures. Again, take pictures. Take tons of pictures. Please take pictures. These pictures can also become a permanent part of the information. You can always attach that to your asset management software, whatever kind of package you're using to keep track of where everything is. Products such as our Fiberbase allow you to attach photos to every database object. So you could have a photo of a building and where the building door is, or a pole and where you've got a possible obstruction. Anything like that. Take photos. Not just the things that I can think of, but the things that we can't think of right now. Take pictures. Then we've got to look at permitting if it's underground, and we've got to look at right-of-ways, pole permits, all of that kind of stuff once we determine the route we want to take. And then we've got to consider our inside plant on both ends. Where are we going to make building entry? And how's that going to apply to the last stuff we were talking about with the inside plant? All of these considerations, all of these are questions to ask. And once you get the answers, believe it or not, the bulk of it takes care of itself. Last topic. What level of protection are we going to give this? Switching protection. With virtual routing, we could go completely unprotected. We could have 1-to-1 protection with multiple protected routes. We could have 1 to whatever. We could have an infinite number of routes depending on the number of switches we go through and how we can do our switching protection in a mesh or a grid. And then we've also got questions of route protection. Rings are a fine example of diverse routing. I've dealt with some governmental entities where we actually had to come in on 2 separate pole lines from 2 different ends of the properties so that we had a total redundant physical route. In case something got dug up or torn down, there was no place that the routes were common. Not even a couple of poles. And then you're also going to want to look at spare fibers. However many fibers you think you need today, I recommend you go 4 times. If you think you need 12, do 48. It's easier to pull a 48 now and have extras than to try to pull another 12 or 24 next year. Then you've got whole routing issues. You've got extra labor. It's cheaper just to go ahead and pull it once and be done. If you need, 72, pull 144 or 288. Just like the extra duct, you can always lease dark fiber as well. Particularly if you're running with some kind of wavelength division multiplexing, you've got a great deal of capacity there for leasing fiber space. And that's a possible revenue stream that you want to look at as offsetting your other costs when you're looking at the cost benefits of the solutions you find to the questions and answers that you get. Lastly, backup power supplies. Do you want to have backup secondary power, wind or solar maybe, or just go ahead and go with the standard backup generator, or battery backup if you're operating mostly on DC? And equipment standbys. Are we going to have circuits that have hot swappable modules, or are we going to have to take down our circuit to do a swap of a module? Hot swappable, of course, means that we can remove a module and replace it without taking down the entire link. So those are some of the questions that you want to ask when you start to looking at the at your equipment needs and your choices. All right, so in part 2, which we will do sometime in the second quarter this year, I don't have the exact date. Now I'm looking at our list here, and no, I don't have the exact date yet for our part 2 of this series. But keep an eye out. We'll be sending out emails, and just keep checking in. But we're going to talk about choosing our components. We're going to calculate loss budgeting. We're going to look at testing and documentation, some preliminary cost estimates, and then some practical considerations. Stuff to look at and make you go, Because really, design and teaching someone to do design isn't about giving you the answers. It's about making you go, And if you're asking the right questions, then you're going to do good design. So thank you all for being here. I see a comment in the chat room, the question box. And Carlos, I'm a little fuzzy on my Espanol, but I think you're saying good afternoon. And I can't tell if you're asking a question about the webinar or thanking me for the webinar. If you could get someone to help you out with get that into English if there is a question involved, I'll be happy to do my best to answer it for you. Remember, the question box is where you want to put your questions and comments. Now, I did get a couple of emailed questions, and I guess the most interesting to me is what generally are the differences between planners and engineers? And that's a semantics kind of situation. Some places say that to be an engineer, you have to have a degree and a license, and if you're not, then you're a planner. What's the difference between the work of the two? Probably not much. Probably not much at all. I talk about plans versus layouts. Again, in the U.S., we've got a lot of semantics issues. Basically, if you're not an engineer, I would go with something more akin to calling it the layout and calling yourself a planner rather than a designer. But each their own. I think the function is the same. There's just a little bit of licensing to call yourself an engineer. Now, the second question I've got here is about the 652D and 675, and I think that was intended to be 657 types of fiber. And a question has just popped up in the question block about the low water peak. And that goes right to this question. So thank you for that question. Um, Low water peak is only necessary if you are using coarse wavelength division multiplexing. I will tell you that straight up. That water peak is not at one of the commonly used standalone wavelengths. We use 1310, 1550, 1490, and 1625 is our four most commonly used standalone wavelengths. None of them are affected by the water peak. The water peak causes an effect when we're trying to do coarse wavelength division multiplexing and we're trying to use all of the wavelengths. If we're only going to use like 3 or 4 or 5 wavelengths in a CWDM system, we can probably still work around that water peak. The low water peak fiber is specifically to open up the entire spectrum for CWDM. And there's a ton of workarounds. So I hope that answers the question. Thank you for that question. Now the 657 fiber, the bend insensitive, the performance there is pretty much on a par with the NZDS. You're going to expect your losses to be 1310 is going to be around 0.35, 1550 is going to be around 0.22 dB per kilometer, and you're going to have 0.25-ish at 1625. And again, those are going to be opening up your C-band and L-band for primarily DWDM circuits. And looking at that dense wavelength division multiplexing, packing 40 to 60 or 100 channels right there in the C and L band. So, all right, got a thank you in the question, so I'm glad that I handled your question and helped you out. Let's see, and one last question came in by email. Again, ask your questions in the question box, or you can email them to training@fiberoptic.com if you want to email your questions, and we'll get someone to get back to you. The other question is how the cable choice affects light transmission. And I think that goes back to the multi-mode or single mode. Multi-mode's just going to go for, multi-mode's going to be a shorter distance. It's going to have higher loss and a lower bandwidth. Your fiber choices for single mode, everything is going more and more to a dispersion shifted or a NZDS. And that NZDS is going to give you the capability of opening up C-band and L-band. It also has a couple of extra properties in that it reduces the effects of polarization modal dispersion, which we're not digging too hard into dispersion in this particular venue. There's other webinars that I do that will talk about that in greater detail. Again, check back into the archives or look for future webinars revisiting some of those topics. But the NZDS or the newer glass does tend to tighten up on the tolerances for core geometry fluctuations and keeps the effects of polarization mode dispersion lower. So I think that answers that question. If there's any follow-up questions that anyone has, again, you can contact us at the email address training@fiberoptic.com, and you can go back into the archives, look at any of the past webinars, www.fiberoptic.com/webinar. So if there are no other questions, I want to thank everybody again for being with us, and look out for part 2 in the second quarter of this year. And it's been a pleasure talking with you. And no other questions. You guys have a great day. Thanks.